Okay, good morning everyone, and welcome back to Math 115. So today we're going to talk about section 2.3, not 2.3. What am I talking about? We're talking about section 2.4, aren't we? We just talked about section 2.3. So homework 2.2 and 2.1, actually there's three homework assignments. There's 2.1, there's 2.2a, and then there's 2.2b, and they're all due today. So that covers everything that we covered basically up to Wednesday of last week. So I extended those due dates. They were due previously on Friday. I extended them to be due today, just in case anybody had to travel or something, or I don't know, your power went out. So that's the homework, and I'm going to post a new homework probably today for 2.3 and also for 2.4. So those are going to be the homeworks that are coming soon. Your next assessment is going to be tomorrow. Okay, tomorrow in class, the last 15 minutes of class tomorrow will be the quiz. That quiz is going to cover sections 1.6, 1.7, 1.8, 1.9, and 2.1 and 2.2. Okay, so kind of a lot of material to cover for that. But the quiz questions, I'll remind you, come directly from the homework assignments. So if you go back and look at your homework assignments for those sections and you know how to do all of the problems on the homework, then you will know how to do all of the problems on the quiz and you'll get an A+. So to remind you, there's no calculators allowed on these assessments. I will take the homework problems and I'll modify the numbers to make them work out nicely so that you don't need a calculator. For my office hours, my next office hours are going to be tomorrow after the quiz, okay? So that'll be from 2:30 to 4 in my office. So that's my next office hours. And then also, if you want to study for this quiz, but you're like, oh crap, my office hours aren't until tomorrow, well, you could schedule an appointment with me if you want, or you can go to the Math Tutoring Center from 10 a.m. to 4 p.m. Monday, Tuesday, Wednesday, Thursday. If you do that, you don't have to work around my schedule. And you can just show up whenever you have like 30 minutes between class. You can go to the Math Tutoring Center and learn some math. Or get some help on your homework problems even. Like, you can probably do the homework problems faster with help than you can without help, and you'll learn the homework better anyways. Okay, so that's the Math Tutoring Center. Are there any administrative questions before we start in on content for today? Okay, doesn't seem like there are. So let me remind you what we talked about last time, and I will not go into this at great length, but last time we learned how to do long division. Okay, so we basically defined what does division mean for polynomials. And what division means for polynomials is basically, if you can take a function and factor it, okay? Then the factors of the polynomial are the divisors, right? So if I divide a polynomial by one of its factors, then I get the remaining factors. Okay, pretty simple stuff. So that's how we defined division for polynomials, and then we saw, okay, how the hell do I actually do it? Okay, so that involved this lengthy process of matching the first term of our divisor with the first term of the dividend via this first part of the quotient, right? And then we subtract and so on and so forth, and then we get a remainder, and then we repeat that process ad nauseum, right? Until we're done, until we get a remainder whose degree is less than the degree of the divisor. That is when we stop. And if the remainder is something less than the degree of the divisor, but still not 0, then that's just our extra little term here, which we put it divided by the original divisor, okay? So this is like our leftover piece, okay? So this is just like when you did 7 divided by 2, and you said, well, this is 3, remainder 1, yeah? Remainder 1. Or you would say, in other words, 3 and 1/2, yeah? So you just put the leftover that of whatever 2 can't evenly go into, you put the leftover just right on top of the original divisor. Same deal with polynomials. So that's division, and that's all I'm going to say about division. Oh, okay, yeah, that's all I'm going to say about division, except for we also have the rational zeros test, which was really important. That tells us, basically, if I have any polynomial, well, the rational zeros of that polynomial are going to have a certain form, okay? Namely, the numerator should be a factor of the ending coefficient, and the denominator should be a factor of the leading coefficient. Okay? So why is this useful? Well, this is useful because we can use it to get a short list of zeros, of possible zeros, which we can then check whether they are actual zeros. So we check whether they are actual zeros by just plugging them into the function, right? So we did that with this example. We found all the factors of 4, and we found all the factors of 3, and then we divided them all by one another and got this short list of possible zeros. And what you can do from there is check one by one by plugging them in to the function, plug them in to the function, plug them in to the function. See, do I get 0? Well, if it's a 0, we should get 0 when we plug it in, right? So, you know, most of the ones are probably not going to be zeros, but it turns out that for this example, one of them is a 0, and that was, I think, 2/3. Okay, so when we plug 2/3 in, it was 0. So why is that useful? Because our goal here is to factor a cubic polynomial. So we don't really have a method of factoring a cubic polynomial. We know how to factor quadratic polynomials. But the key here is if I can guess one of the zeros using the rational root theorem, then I can divide out the corresponding factor. So I can divide out the corresponding factor here, and I will get a quotient which is quadratic, because if I divide a degree 3 polynomial by a degree 1 polynomial, I will get a degree 2 polynomial. Okay, so that was why the rational root test is useful, is we can use it to guess a factor of a higher degree polynomial. And you can do this multiple times. For example, I had this partner practice that we didn't get to, but would be good practice for you to do on your own, where you can guess some factors. Okay, no, not this one, sorry. This one. You can guess some factors of this polynomial by using the rational root test. You take a look at the factors of 6, you take a look at the factors of 1, right? And then one of those is going to be a root of this polynomial. Once you find it, you do the division. If you do the division of a degree 4 polynomial by a degree 1 polynomial, I will get a degree 3 polynomial. Then I repeat that process. I use the rational root theorem again to guess another one of the zeros. And then finally, I'll have it down to a quadratic, which I can factor normally. Okay, so I just pop off zeros until we get degree 2, and then we can just do regular factoring. So any questions on long division or rational root test or factoring polynomials of degree higher than 2? Okay, if not, then we'll move on to today's class. So today's class is going to be on rational functions. Well, today's going to be the first class of probably several classes which we're going to spend on rational functions. So, well, what is a rational function? We should already kind of have an idea of what a rational function is going to be. It's going to be a quotient of polynomials, right? Just like how we defined rational expressions earlier in the appendix chapter. So we take a polynomial on top, we divide by a polynomial on the bottom, we call the resulting division a rational function, coming from the word ratio, meaning fraction. So the numerator and the denominator should be polynomials. I hope it goes without saying that d should not be 0. But I'll write it anyways. Okay, so that's a rational function. So let's talk about what is the domain of a rational function going to be. Well, remember, a rational function is just the quotient of polynomials. So can someone tell me first of all, what is the domain of a polynomial function? Very good. It should be all real numbers. So, question for the class. Should the domain of a rational function, which of course a rational function is just a quotient of two polynomials, so should the domain just be all real numbers as well? What do we think? I'm hearing a lot of no. Can someone explain why no?
Because it can't be 0, so that would be like the domain.
Yeah, Griffin hit the nail on the head. We need to exclude any values of x which make the denominator 0. It's possible that there are no such values, right? Say if we had d of x equals x squared plus 1, right? That's a parabola which is altogether above the x-axis. It never touches the x-axis. It doesn't have any zeros, right? So that's a situation where we wouldn't worry about the denominator being 0 because the denominator can never be 0. So it's possible that our domain of our rational function is all real numbers. But what we should really do is be a little bit more careful. We should instead say the domain of a rational function is going to be all real numbers except, I'm going to do this little slash. Okay, this little slash means I'm going to remove from the real numbers the set of numbers x such that those numbers make d of x equal to 0. So that's what this means. It means the numbers x such that d of x equals 0. Okay, that's these numbers. So, in particular, if for example, if d of x equals x squared minus 1, then the numbers x such that d of x is equal to 0 would be the collection of two numbers. What two numbers make this polynomial to be 0? 1 and negative 1, right? So I would take the real numbers and I would remove 1 and negative 1 because those would be the numbers which would make the denominator 0, which is not allowed. Okay, so that's the only thing we have to worry about with rational functions is we have to take extra care to remove any x values which could make the denominator 0. Any questions on the domain of a rational function? So I have a question. Maybe someone can help me. So remember, when we were talking about domain, there were like two things that I need to worry about when I'm talking about the domain of a function, right? The first one was I don't want to do any dividing by 0. Someone remind me what the second one was that I need to worry about? I can't do square roots of negative numbers. I didn't say anything about doing the square root of a negative number for the domain of a rational function. Can someone explain why that is? Why don't I need to worry about doing square roots of negative numbers? Is it possible that I could have a rational function that has like a square root somewhere in the top or the bottom? All right, this one seems to be stumping you all. Okay, can someone remind me what is the definition of a polynomial? If n is a polynomial, what should it look like?
X squared plus 2x plus 1.
Sure, something like, okay, that's an example of a polynomial, x squared plus 2x plus 1, dot, dot, dot. What are the main features of a polynomial like this? Well, yeah, smooth and continuous graph, which is by virtue of the fact that, okay, this is going to be something like a n x to the n plus dot 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 plus a1 x plus a0, yes, and the bottom will be something like bm x to the m plus dot 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 plus b1x plus b0, right? But there's something crucially important about the powers n and n minus 1 and n minus 2 all the way down to 1 and 0. They must be whole numbers, right? And what is a square root? A square root is a 1/2 power. So, now can someone put it together and explain why I don't need to worry about square roots when I'm thinking about the domain of a rational function? Yeah, because square roots functions, or sums of square root functions, are not polynomials. And the numerator and the denominator are both polynomials, as defined by this definition. So if the numerator and denominator are polynomials, I know there's not going to be any square roots anywhere in this whole function. Okay, so that's why I don't need to worry about that other piece of the domain puzzle. Okay, I just need to worry about, well, is it possible that I divide by 0? Okay, so that's a pretty heavy theory question, but we made it through. But I feel like these things are important to kind of connect this sort of web of understanding, to know that this all has like very strong connections everywhere together. It's not A implies B implies C implies D. It's all over everywhere. There's arrows going every which way. Okay, it's all interconnected. Okay, so that's the domain of a rational function. So now let's talk about vertical asymptotes. Okay, so an asymptote is really just a location on the graph of the function where the function blows up. Okay, or it could blow up in a negative way, right? So for example, the easiest function that you know of that has vertical asymptotes is, think f of x equals 1 over x. Okay, what does the graph of that look like? Well, as x approaches 0, we're dividing by an extremely small number, which means dividing by an extremely small number is the same as multiplying by an extremely big number, which is why when x gets close to 0, the function value goes really, really crazy high, and really, really crazy low if we plug in something like negative 0.0001, right? Then we're dividing by an extremely small number, so this number will have a very big value altogether. So this is what happens when we have a vertical asymptote. So in math speak, what that means is a rational function will have a vertical asymptote at an x value. Of course it has an x value because we're talking about, essentially, we're thinking, well, there is a vertical line. Okay, there is a vertical line here. In this case, it's x equals 0, right? To which my function is getting, or the graph of my function is getting arbitrarily close. Okay, it's going up, 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 and it's getting closer and closer and closer and closer to that vertical line. So another vertical asymptote somewhere else is also going to be another vertical line, and vertical lines are defined by their x value because their y value can be anything, right? But all of the x values of the points on a vertical line are the same. So we define a vertical line by the equation x is equal to a, where a is a real number, okay? So a is in the reals, okay? So it's a number. So let's define this notation now. So we say that that's true if the limit, if the limit as f of x, if the limit as x approaches a, and I put this little minus sign here, okay? What does that minus sign mean? A minus means approaches a from the left. And then a plus is approaches a from, guess where? The right. Okay, so this is a little bit more limit notation, okay? And by the way, in the book and consequently in the homework, what they do instead is they say something like, okay, they say as x goes to a to the left, comma, f of x goes to infinity. Okay, I hope that it's not too confusing that this notation means the same thing as the notation I'm using in class, namely this one, right? Limit as x goes to a from the left. That means a is going to a from the left, which is what's written here, right? And what happens when x goes to a from the left? Well, f of x goes to infinity, right? So that's what's written on the right side, okay? So hopefully that's not too confusing, but there is that difference in notation between the book and the homework and my class. It is beyond me why the book would not use the standard notation, but apparently that's the choice that they made. I guess they were trying to dumb it down or something. I'm not really sure what was happening with the book, but it really feels like extra steps in terms of just like making you learn an entirely new thing for no reason, because as soon as you get to calculus, you need to use this notation anyways. So anyways, these are the sorts of things that I spend a lot of time thinking about that you don't really need to worry about, so I'll shut up about it. So if the limit as x approaches a from the left of f of x equals plus or minus infinity. Okay, so here's a situation where here's a, and here's a situation where f of x goes to infinity as x approaches a from the left. So the x values get closer and closer and closer to a. The height of the function gets closer and closer and closer to either positive infinity or negative infinity. So you can see the height here is going up, 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 right? Okay, or you could have something that looked more like this, right? Going down, 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 down. So either of those, okay, define a vertical asymptote. Or we can also have the other thing be true as we approach from the right. So the x values gets closer and closer and closer and closer and closer from the right, and the function value either blows up this way or it blows up this way. So these are the four options. Okay? If any of those four things happen, we say that r of x has a vertical asymptote at x equals a. All right. Any questions about the definition of a vertical asymptote? Okay, so we defined what it means to have a vertical asymptote. Now let's talk about when it's going to happen. Well, it's going to happen, basically, what is the feature of 1 over x that makes it have a vertical asymptote at x equals 0? The feature of f equals 1 over x is that when x gets close to 0, the denominator is getting close to 0, right? If the denominator is close to 0, then this number, which is a number divided by that denominator, is getting huge, right? It's getting massive, like negative infinity or positive infinity. So that is the feature of f of x equals 1 over x that causes the vertical asymptote, okay? The vertical asymptote is here because if you plug in that value into the function, I get 1 divided by 0, which is not defined. So as you get close, you expect the behavior of the function to be really kind of crazy because you're almost dividing by 0. You're almost dividing by 0. So, same deal with other functions, okay? So, we will have a vertical asymptote. Okay, I should make my notes a little bit cleaner, which should say r of x has a vertical asymptote at x equals a if x equals a is a root or a 0 of d of x, the denominator. So if a is a value which makes the denominator to be 0, then we will have a vertical asymptote at that point. So what does that mean? Well, that means that x minus a is a factor of d of x. We've talked about this all the time. X equals a is a root or a 0 means x minus a is a factor. Okay, so let's see how that works for this one. Well, if I were to factor this, what would I get? X on the top is already factored, but if I were to factor the bottom, I would have x plus 3 and x minus 1, right? Okay, which means I will have a vertical asymptote at x equals negative 3 and x equals positive 1. So let me draw those on here. X equals negative 3 is here, and x equals positive 1 is here maybe. This is x equals 1, this is x equals negative 3. So these are where my asymptotes are going to be, okay? So I'm going to have some kind of behavior like this maybe, or something like that, okay? That could be something that we have, I don't know. But let's see. I mean, we can check by asking ourselves, well, if I plug in a number which is really close to 1 but less than 1, then what is the value of the rational function going to be? Well, the top would be something like 1, or like, okay, let's say really something really close but less. So let's try 0.99. We would get 0.99 on top, and on bottom we would have what? 3.99 times what? What would go in here? If I plug in x equals 0.99. Sorry? Yeah, it should be 0.01, but negative. Yeah? So, what kind of number is here on the bottom? It's a negative number, and really small. The top is a positive number, and not necessarily really small, right? So what is this behavior? This behavior is going to infinity or minus infinity? Yeah, minus infinity, right? Because it's a negative number, okay? Positive number divided by a negative, or by a positive number times a negative number. That means we have a positive over a negative, and the bottom is small, which means the whole number altogether is huge. So this is going to like a minus infinity here. Okay, if you want to check what's happening on the other side, just plug in something like 1.01. We'd get 1.01 on top. On the bottom, we would get 4.01 times 0.01, but positive this time. So what's happening on the right side? We're going to infinity. Yeah? Okay, and then on the other side, let's try the other one. Well, if I plug in like negative 2.99, the numerator will be negative. This number will be positive. And then the bottom, this one will also be negative. So we'll have negative. Okay, let's actually do it. Negative 2.99 on the top, divided by, if we add 3 to that, we would get 0.01. And if we subtract 1 from negative 2.99, we would get negative 3.99. So the numerator is negative, the bottom is also negative, which means altogether it's positive, which means it looks something like that. Okay? Something like that. And then if we think about what happens on the far left, well, we plug in something like negative 3.01, we would get negative 3.01 on the top, and on the bottom we would get negative 0.01 times negative 4.01. So this number altogether is negative. So something like this is probably what this looks like. Okay, so this is how we can get an idea of how these vertical asymptotes are looking. We're going to make this more specific in a second, so I'm not going to belabor this point. But we'll talk more about that in a second. But this is how we can identify where are we going to have a vertical asymptote, okay? Is we just check the locations on the x-axis that cause the denominator to be 0. This is where we're going to have a vertical asymptote. Yeah?
So the one in the middle, we're going to connect.
Right. So the graph of a rational function, except for the places where we have a vertical asymptote, the graph of a rational function is going to be smooth and continuous. Okay? So it's going to be smooth and continuous except at the spots where we have a vertical asymptote. So that's why I connected those. Okay. So, any questions on this so far? Any other questions, I should say? All right, then let's talk about horizontal asymptotes. We already talked about vertical asymptotes. So what does it mean if we have a horizontal asymptote? Well, the horizontal asymptote is going to be a horizontal line, y equals to k. So what does the line y equals to k look like? Well, the y value is fixed, and the x value can be anything it wants. So that causes us to have a horizontal line. What if I made this dashed? There we go. So this is the line y equals k. So what does this look like? Well, we say that r of x has a horizontal asymptote if the limit as x goes to infinity of f of x is equal to k. Okay? Or the limit as x goes to minus infinity of f of x is equal to k. What's the difference between this one and the one before? Well, before we had x going to a given x value, then the function value goes to infinity. Now we're saying we're going to let x go to infinity, and the function value becomes a number. Okay, so that's the difference here. It's about whether the x is going to infinity or whether the y is going to infinity, right? So in this case, a horizontal asymptote would look something like, it could look something like this, maybe, okay? This would be a situation where we have limit as x goes to infinity equals k. Or it could look like this, right? That would be the limit as x goes to infinity of f of x equals k in a different way. Or we could have it on the other side. Limit as x goes to infinity, negative infinity of f of x equals k. What would that look like? Something like this. Or like this. Okay? And it's possible we would have different asymptotes on either side, okay? We could have something like this as well, where we have, say, two different horizontal asymptotes, one on the right side and one on the left side, which are different. And maybe the function looks something like this, right? That could be a function. I shouldn't have made that dotted, but you get the idea. So we have a horizontal asymptote at y equals k if one of these two things is true. Either we approach that number as x goes to infinity, or we approach that number as x goes to minus infinity. A really common horizontal asymptote is 0. Okay, so often the function gets really close to the x-axis as we go to infinity. You'll see why in a minute. But are there any questions on the straight-up definition of when we have a horizontal asymptote? Okay, so I'm bringing in more and more of this limit notation. Okay, so I know this is kind of confusing if it's the first time you've seen it, but what you have to think about is, well, I'm not thinking about plugging in infinity. There's no plugging infinity. I'm just plugging numbers successively, which are larger and larger and larger and larger. And I'm noticing whatever trend is happening in the output, okay? So for example, if I plug in 1,000,000 and I get 0.01, and then I plug in 2,000,000 and I get 0.001, and I plug in 5 billion and I get 0.0000001, right? Then the pattern here is that as the input gets larger and larger and larger, the function value is getting closer and closer and closer to this number k. Any questions on horizontal asymptotes so far? Okay, then let's see. Yeah, sorry.
Is there a way for there to be a vertical asymptote without a horizontal one? Or do they both? Or is it like if one is there, the other one is always there too?
Let me think about that. Well, I mean, you could definitely have something like that with a piecewise function. For example, so the question is, do horizontal asymptotes and vertical asymptotes always come together? The answer is no, sometimes they don't. For example, we could have the function, I'll show you some functions actually in Desmos. Say we had the function, okay, we're gonna do like x cubed minus 2x squared plus x plus 1. Okay, so here we have a cubic function, and then we're going to take all of that. We're going to take all of that and make a rational function out of it by dividing by, I don't know, how about x squared minus 1? Uh-oh. Check that out. Here's a situation where we can see the graph has multiple vertical asymptotes, right? It has two vertical asymptotes, one where x is equal to 1 and one where x is equal to -1, because that's what would make the denominator 0, right? But what do we see? Do we see that we have a horizontal asymptote? No, we don't, because if we had a horizontal asymptote, then this, we would expect us to like bottom out, get to a certain value of x as we get really, really big. But what happens as we go really far away is we just observe linear growth, or linear decay as we go to the left, right? So we just have linear growth. So there's no asymptote because there's no number that the height of the function's getting really, really close to. It just keeps getting bigger and bigger and bigger and bigger. It's not like evening out at a certain point. Okay, or it's not evening out and going to 0 or something like that. That would be a horizontal asymptote. So here's an example of a function that has vertical asymptotes but not any horizontal asymptotes. If you wanted to see a function that has horizontal asymptotes but no vertical asymptotes, I hope you'll allow me to bring in an exponential function before we've even talked about exponential functions. But we're going to take this exponential function to the power absolute value of x. No, negative absolute value of x is what I need. So I need a minus sign here. Okay, so what does this function look like? It looks like this. It kind of looks like a tent or something, right? So as x becomes 0, this becomes e to the 0, which is 1, right? And as x gets bigger, well, whichever direction we go in is always going to be a positive, and e to the minus something is going to be 1 divided by e. So as we go, it gets smaller and smaller and smaller in that direction, smaller and smaller and smaller in this direction. So I think that fully answers your question. Sometimes we will have horizontal asymptotes when we don't have vertical asymptotes, and sometimes we'll have vertical asymptotes when we don't have horizontal ones. We all happy about that? All right, cool. So that's what I want to say about that. So now okay, are there any other questions about asymptotes so far? Yeah, Liv?
So we have one and not the other. Will there ever be like a question to ask us if we don't have?
Okay, the question is, will there ever be a question that asks about the existence of horizontal or vertical asymptotes? Yes, I don't know if it will specifically say, are there both, neither, or one or the other, but I mean, you can check the homework. You know exactly what questions are coming. You can click on the homework assignments ahead and look through and see, and all the quiz questions and exam questions come directly from the homework, so nothing will be a surprise. Does that answer your question? Any other questions? Okay, then let's move on and talk about graphing rational expressions. And the first type of rational expression which we are going to graph is we're going to think of the rational expression as a transformation of 1 over x. Okay, so this doesn't work for every rational function, but it works for some. Okay, let's see how, right? So we remember, hopefully, that 1 over x was one of our celebrity functions, right? So if we had something like this, well, this is just a transformation of a celebrity function. We know how to graph the celebrity function, so all we have to do to graph the transformation is to move it over or up or stretch it or reflect it or do whatever we need to do according to our transformations, right? All right, so let's talk about this function as a transformation of 1 over x. And if we want to think about it as a transformation, I need to think about what transformations. What are my transformations that I have to do here? Sorry? I have a +1 inside my parentheses, right? So this is a left one. That's a horizontal shift. Anything else? It's negative. What is the negative going to do? It's going to be a reflection about which axis? Well, is the negative sign in my parentheses or outside of my parentheses? It's outside of your parentheses, right? If I have something going on outside of the parentheses, does it have to do with the up and down world or the left and right world? Yeah, when it's outside the parentheses, we're always talking about up and down, okay? So if I have like a +3 or something right here, see, it's outside of the parentheses. That would give me a vertical shift, up and down. All the stuff that happens on the outside is always an up and down transformation. So that means we have a reflection about the x-axis. Anything else? The 2. What is the effect of the 2 going to be? Well, it's outside of the parentheses, right? So what is going to be having to do with the vertical world, right? It's going to be a stretch or a shrink. It's going to be a stretch because the number is bigger than 1. So this is a vertical stretch by 2. Okay, so I'm going to draw 1 over x first. So this is 1 over x. Okay, this is 1 over x. So what do I need to do? I need to do these transformations. Is this the correct order, by the way? Yeah, I think the stretch needs to go first, right? You're going to have to go back to the rainbow slide and think about the order which we do these in. I think... Whoa, now I'm second guessing myself. We better go back and check. What section was that? Here we go. It's right here. Okay, yes, so vertical stretch needs to go first before reflections. Technically, actually, these 2 steps can be done in any order, but that's the order that we put them in arbitrarily. Okay, so vertical stretch comes first, then reflection. Okay, so first off, let's move it left 1. Okay, what does it look like if I move the whole thing left 1? Well, instead of having a vertical asymptote at x equals 0, we're going to have a vertical asymptote at x equals 1. So we're going to move all together to the left. Okay, 1 unit. So it's going to look more like this. Okay, that's left 1. Then we have to do a vertical stretch by 2. So that means we're going to just go up faster, and we're going to go down faster, okay? And then we're going to reflect about the x-axis. Okay, so my new asymptote is going to be at x equals to -1. And my function is going to look not like this, but it's going to look like this because of the reflection. And also, it's going to be steeper. So it's going to look more like, I'm going to exaggerate this here somewhat. Okay, so one thing you'll notice is that these 2 points are much closer to the point on the asymptote than are these 2 points as it compares here, right? So why is that true? That's true just because, look, we're going to decay much, much faster. We're going to grow much, much faster because we're thinking about twice the rate of growth, basically, or twice the rate of decay. All right? So that's a transformation of 1 over x. Any questions on that one? All right, let's see one more. Uh-oh. What is this function? This function is kind of weird, isn't it? I thought we were doing transformations of 1 over x. Is this a transformation of 1 over x? Well, is there anything that's bothering us? What's bothering us? Yeah, there's an x in the numerator. That's not a transformation of 1 over x. Except, we can think about this as a transformation of 1 over x if we apply long division. It's going to be a really short long division. So what would I do? I'd multiply 3, correct? So then I would subtract 3x minus 3 here from this. And what would I get when I do that? I would get, these 2 would go away, and I'd have -2 minus -3. That's 1, right? So this whole long division is equal to 3 plus 1 over x minus 1. Now it looks like a transformation of 1 over x, right? Now it looks like a transformation of 1 over x. What kind of transformations do we have? We have right 1 and up 3. Yes? Vertical shift and a horizontal shift. So let's graph it. Instead of having asymptotes at x equals 0 and at x equals 0 and y equals 0, we're going to have asymptotes at x equals 1 and y equals 3. So instead of looking like 1 over x, we're going to have an asymptote at, we're going to have asymptotes at x equals positive 1 and and y equals positive 3. Yes? And so our function will just look like this. No, that's not correct. I'm sorry. Look like this. Okay? That's 2 examples of a way that we can graph a rational function by thinking of it as a transformation of the function 1 over x. Okay, so next time in class what we're going to talk about is more graphing, basically. So we'll do some more graphing, and we'll talk about holes and some other stuff. Don't forget, we have a quiz in class, the last 15 minutes of class tomorrow.